Okay, let us resume our afternoon session. Okay, for the next talk, we are happy to have Konstantinos Roumpedakis, who will tell us about non-invertible symmetries in Maxwell theory, part 1.
Thank you very much. Thank you very much. I would like to also thank the organizers for putting together this very nice workshop. So I'm going to talk about non-invertible symmetries in Maxwell theory. Why do we care about Maxwell theory? Actually, we don't. But this is a very simple theory where we can actually try to develop some new methods for studying non-invertible symmetries, and that actually is going to be our goal for today. I'm going to, in the first part, I'm going to argue that Maxwell theory has 3 infinite sets of non-invertible symmetries, which can be constructed either by higher gauging or half-space gauging, which, although I'm sure that everyone is familiar with, I'm going to review anyway. And yeah, this is the first. This is the first of a 2-part talk. The second one will be given right after by Pierluigi Niro, which during the second part, which is the main goal of our work, he will give a new. Well, he will give a different way to realize those symmetries in a unified way, both non-invertible symmetries obtained by higher gauging and half-space gauging. Yeah, in a unified way, which will be very elementary, and we will be able to calculate fusion rules, how they act on lines, and so on. So let me start with some motivation. So non-invertible symmetries are they're long known to exist in 2 dimensions, and they can actually be quite useful for constraining the dynamics of 2-dimensional TQFTs. And basically, in 2 dimensions, we look for non-invertible symmetries using bootstrap techniques. And the main question is how do we look for non-invertible symmetries in higher than 2 dimensions? And that will be our goal for today will be to try to develop a slightly more systematic way to look for non-invertible symmetries in the case of Maxwell theory. Yeah, of course, we are familiar with we are interested in non-invertible symmetries because at the end of the day, we want to use those to see if we can learn anything new about the dynamics of QFT. And for the last year or so, there has been a lot of work in using non-invertible symmetries in holography, and I personally think that non-invertible symmetries can play an important role in the case of ADS3 CFT2 correspondence, but this is a different story. For today, we're going to focus on Maxwell theory in 4 dimensions. So let me start with some history. Well, as I already mentioned, non-invertible symmetries are long known to exist in 2-dimensional RCFTs, and in the last 3 years, there have been many examples in higher dimensions where people constructed the non-invertible symmetries. And in all the examples that I know of, including the chiral symmetry, the chiral symmetry case, the non-invertible symmetries are constructed using 2 different ways, namely higher gauging and half-space gauging. I'm going to quickly review these 2 procedures, although that might be a bit boring for most of you. But I'm going to review them anyway, and then we're going to apply these two procedures, and I'm going to argue that even Maxwell theory has, as I already mentioned, 3 infinite sets of non-invertible symmetries, and the goal of the second part will be to realize those symmetries in an elementary way using Lagrangian. Yeah, so let me start with reviewing what higher gauging is. So to define higher gauging, let me take 1 step back and review what ordinary gauging is. So in the ordinary case, we have a symmetry G, And to gauge it, we introduce a gauge field little a, and in the path integral, we sum over it. Using Poincare duality, we can convert this sum over cohomology as a sum over homology. And at the end of the day, what we are doing is we sum over defects generating the symmetry G along all the possible non-trivial cycles of our space-time manifold M. So by Harry gauging, we define as the gauging of a discrete Q-form symmetry on a codimension P submanifold sigma. And analogous to the ordinary case, what we're doing, we basically sum over insertions of the defects that generate the symmetry G along the non-trivial cycles of a surface of a submanifold sigma. Okay, let me give a bit more intuition. To do so, let's focus on 3 dimensions and let's consider a one-form symmetry. So in this case, we have a line generating the one-form symmetry, and we can gauge it along a surface, along a 2-dimensional surface. So we basically what we do, the sum that I wrote before, is equivalent to creating a network of lines along a 2-dimensional surface. And the main goal is the basic point here is that we are gauging the symmetry only on a surface, so the bulk still remains the same. And the only thing that we do is we create topological defect along the surface. We typically refer to these surfaces as condensation defects. And as a matter of fact, they do not act on local operators because we can always pass through a local operator through the network. But they do act on line operators, like in this picture, where we have a line. This is not necessarily a topological line; it can be a Wilson line. And when it hits the network, it gets transformed into a new line. Let me show you how we can explicitly calculate fusion rules for condensation defects, which later we're going to use in the Maxwell theory. So again, let's focus on 3 dimensions to be able to draw some pictures. And let's consider a Z2 one-form symmetry. So we have a line eta, whose square is 1. And we define the condensation defect by this sum. So here we choose a surface sigma, and we sum over insertions of the line eta along all the Z2 cycles of sigma. And we have also introduced a normalization factor just for convenience, which, as also Luigi mentioned, we can change it by sticking an Euler counter term of sigma. If we choose sigma to be a torus, so now we have 4 different four Z2 cycles. This sum becomes the sum of these 4 terms: the identity line, the line along the A cycle, the line along the B cycle, and the eta line along the A plus B cycle. And now it's a simple exercise to take the square of this expression and show that S times itself is 2S, which shows that S is non-invertible. Okay, so similarly to the ordinary gauging, there can be obstructions to gauging a Q-form symmetry on a codimension P manifold. And we say that a Q-form symmetry is P-gaugeable if it can be gauged on a codimension P gaugeable if it can be gauged on a codimension P manifold. Otherwise, we say it is P anomalous. The usual case of a Hofft anomaly corresponds to a 0 anomaly in this language. And there are interesting cases where, although there is a 0 anomaly and we cannot gauge the symmetry in the whole space-time, we can still gauge it on a submanifold. And this actually is going to be also the case in Maxwell theory, where we have the 2 one-form symmetries. We know that there is a mixed Hofft anomaly between them. We cannot gauge both of them at the same time, but it turns out that there is no one anomaly, and we can pick any subgroup of the one-form symmetry, engage it along a surface, and define a condensation defect. Okay, so let me now quickly review what half space gauging is. I think it already appeared in 2 talks, but let me quickly review it. So let's start with a theory with a one-form symmetry G1 and also a duality group GD. This in a moment, this is going to be our SL2Z duality group in Maxwell theory. And we make the following observation: if there is a subgroup AH of the one-form symmetry and the duality element G2, such that if we start with our initial theory, we gauge the subgroup H to get some TQFT, QFT prime, which is dual back to the original theory, then we can construct a topological defect in the following way. We can split our space-time into 2 parts. And just on one part, let's say the right part here, we can apply these 2 procedures. And after we do so, on both sides of the defect, we have the same theory. And again, the only thing that we have achieved is to create a topological defect in the interface. The properties of these duality defects are specified, of course, by H and G2. In fact, the action on local operators is fixed by the duality element, and the action on line operators is fixed by the subgroup H that we are gauging. Basically, this half space gauging procedure is a way to turn dualities into symmetries. This is actually it is actually a well-known fact in the compact scalar theory in 2 dimensions, that we have the duality at the self-dual point is a usual invertible symmetry, and away from the self-dual point, we can still define a topological operator acting as a duality, but at the cost of making it non-invertible. And basically, this procedure is the analog of T-duality in 2 dimensions, where we can turn duality transformations like S-duality into a symmetry. Okay, so let's finally talk about Maxwell theory. Okay, so we start with this Lagrangian, where F is the usual field strength of the U1 gauge field, and we're going also to include a non-zero theta term, and we're further going to group the 2 couplings theta and E squared to a complex coupling tau. As we all know, Maxwell theory has 2 one-form symmetries: U1 electric one-form symmetry, whose current is F tilde, the dual field strength given by this combination, and also a magnetic one-form symmetry, whose current is just F. Maxwell theory has also an SL2Z duality group, which basically which acts on the electromagnetic charges N and M in this way, and on the couplings like this. Okay, so let's now apply the 2 procedures that I described before, namely higher gauging and half space gauging, and construct topological defects in Maxwell theory. First of all, we know that the U1 one-form symmetry, there is no self anomaly. It doesn't have a self anomaly, so we can choose any ZN subgroup, any ZN subgroup, and condense it and gauge it along a surface. And in this way, we can construct an infinite set of condensation defects labeled by an integer n. Using what I described before, we can easily study the fusion rule of these defects, and it turns out to be something like this, where here we have a condensation defect obtained by condensing a Zn subgroup of the one from symmetry. This is a condensation defect obtained by gauging a Zn prime subgroup of the one from symmetry. And their fusion is another condensation defect times a number which depends on the topology of sigma. It is basically a partition function of a TQFT. We can do the same thing for subgroups of the magnetic one from symmetry and define another infinite set of topological defects. And as I already mentioned, we can also pick any subgroup of the electric and magnetic one from symmetry because there is no one anomaly, and construct more condensation defects. In fact, if you take a condensation defect of this kind and fuse it with a condensation defect of that kind, you actually get a condensation defect that you can get by gauging a subgroup of electric and magnetic of the electric and magnetic one from symmetry. Yeah, so that's about condensation defects. Let me now move to duality defects. So let me quickly review the S-duality case, which we're going to generalize for a moment and try to not just S-duality, but trying to realize defects that implement SL2Z. So this group of people, about 2 years ago, they made the observation that when tau is equal to I times an integer, we can define a topological defect that acts like S-duality on line operators. So let me review the argument. So first, we observe that if we gauge a Zn subgroup of the electric one from symmetry, this is equivalent to rescaling the gauge field by 1 over n, or equivalently rescaling tau by 1 over n squared. And yeah, let's recall also how S-duality acts, yeah, which sends tau to minus 1 over tau. So now the observation is that if we start with Maxwell theory at tau equals I times an integer, we can gauge the Zn subgroup of the one from symmetry. So we arrive at Maxwell theory at tau equals I over n, which we can map using S-duality back to the initial theory. And now the question becomes whether we can we can construct more duality defects acting on local operators like SL2Z by mimicking this story here, not using just S-duality, but more general duality elements. And the answer is going to be yes. So let's consider a two-dimensional SL2Q matrix given here, where all these numbers NL, NR, and L are rational numbers. And we're going to consider this matrix acting on tau, on the complex coupling tau, and I'm going to argue that the action of this matrix on tau can be realized as a series of duality transformations and gaugings of the one from symmetry. Okay, so let's make the observation that we can decompose this matrix in this way, where X, Y, and Z are all rational numbers given in terms of the n's that I had before. So let's start first with the middle element here. The action of this element on tau. So this transformation sends tau to Z squared times tau, and it can be realized by gauging a ZQ times a ZP subgroup of the one from symmetry. So here we're going to gauge this subgroup in half space, but I forgot to mention that P and Q are co-prime, and so there is no anomaly, and we can gauge this on half space. So the middle element here can be realized by gauging this subgroup of the one from symmetry. So let's now see how we can get the actions of these two matrices. This is just T-duality, but at rational X, which can be we can get by combining the usual T-duality with, but first starting with the gauging of the magnetic ZQ1 from symmetry, combined with the usual T-duality, and then gauging a ZQ subgroup of the electric one from symmetry. And lastly, U is basically S times T. So at the end of the day, we can realize this SL2Q matrix acting on tau with a series of gauging subgroups of the one from symmetry and elements of SL2Z duality group. So now we can play the game of half space gauging, and we notice that if tau is given by this combination, the action of the matrix that I wrote before leaves tau invariant. It's a simple exercise to show that acting on this tau with the SL2Q matrix that I wrote before leaves tau invariant. So now we can play the game of half space gauging and realize reconstruct an infinite number of non-invertible symmetries of non-invertible duality defects at these values at any rational value of theta and e to the fourth. So moreover, the action on these operators, as Luigi is going to show us in a while, it acts on local operators. This defect, they generate an SO2 rotation on local operators. So their action on local operators, namely F and star F, is invertible, and it is an SO2 rotation, but it's an SO2 rotation, but with rational values of cos phi the SO2 angle. But the action on local operators on Wilson and Hopf lines is non-invertible, as we're going to see very soon. So the summary is that even in Maxwell theory, we can use either a higher gauging or half space gauging and construct three infinite sets of non-invertible symmetries. One by gauging subgroups of the electric one from symmetry. The second one by gauging subgroups of the magnetic one from symmetry. And now a third infinite set, which basically acts like an SO2 rotation on F and star F, but on local operators, and is invertible because of the action on line operators. So next, the main
Regarding this last class, I didn't understand. So if once you fix tau,
yes,
do you have an infinite number, or there is an
yes,
infinite number of taus for which there is
no. We fix tau. So basically, we have three rational numbers here. So we fix theta and into the fourth, and we have a third rational number, which actually gives all rational numbers of cos phi. So for fixed tau, we have an infinite set of defects acting on local operators as SO2 with rational cos phi. So I argued that these topological defects exist using higher gauging and half space gauging, and the main point of our our work will be to give you a more elementary way to construct this all these defects in a unified way by giving what we call a Lagrangian, a defect Lagrangian, which is going to allow us to actually compute. It's going to allow us to compute also the diffusion and the action line operators, and hopefully we hope that it might be useful to construct non-invertible symmetries, even in the case where the defects cannot be obtained by higher gauging or half space gauging. But so far we have only we have used Maxwell theory as a toy example. Thank you.
alpha. So
Okay.
one thing you can also consider is to gauge on null space with discrete torsion. No, that's obvious generalization. Do you get more, or it's
No,
inside?
these are actually specific.
It's inside.
Yeah, these are inside
Okay,
the
okay.
dual difference. Actually, the these metrics alone can be obtained by gauging a magnetic subgroup.
Okay, okay.
So these are all included.
And the second question, is there some value of tau for which you only have a finite number of symmetries instead of this infinite number?
Well, for all values of, you are talking about the duality difference, because the condensation ones you have.
Yeah, just duality defects. The condensation I don't care, but I mean, okay, sorry. No, so
You're being recorded.
So for all the values that you've listed here, no, that these three numbers, no?
Yes.
There are always infinitely many types of duality defects.
All these three numbers are independent. Yeah.
Okay, so there are always this infinite number of duality defects. Okay.
I didn't understand the comment in the very beginning about Euler counter term on 2 torus. Can you elaborate on that?
Okay. Here. So here I'm just saying that we can redefine S by sticking a factor exponential of the integral of the rich scalar of sigma, which will effectively change coefficient.
But this is a 2 torus, right? Oh, I see. So yeah, that formula is for generals.
Yeah, this is supposed to be for general. Okay. This fusion rule is only for T2. The fusion rule actually depends on sigma. Then we get a different number here for a different sigma.
I see. So this normalization does not affect the 2 torus case. Okay. That's I guess what it is.
Did I understood correctly that the final non-invertible symmetry reconstructed by alpha gauging acts on f and star f as a SO2 rotation on f?
Yes.
But why this does not violate the flux quantization?
Well, so you are worrying about the fact that if we have a surface integral of f and we drag through the surface, that
I'm worried about the fact that, I mean, typically the integral of f and star f is quantized. If you rotate with a rational angle, they are no longer quantized.
yeah, well, this is the same phenomenon where you.
Oh, okay, I see. I think.
The questions.
Are there any nice arithmetic properties for, say, the partition function or the J function for these magic values of tau?
We spent some time to that, but well, it's too complicated. We couldn't understand why. Well, I don't know. Maybe.
Actually, so if for fixed tau you start fusing these defects, you'll get defects of the same type.
Yeah. Except if you fuse two defects with phi minus phi, then you will get some condensation defect.
Other questions? If not, let's thank the speaker again.
Hello? Okay.
No. I hope. Right.
Okay. You ready?
Yeah.
Okay. Our next talk is by Pierluigi Niro. He will tell about the second part of non-invertible symmetries in Maxwell theory.
Right. Okay, let me join the other speakers in thanking the organizer for a nice workshop and inviting me to speak. And let me also thank Konstantinos for introducing this topic. And he left for me the easy part, which is about defect Lagrangians. So, so the goal here is to try to use a very simple approach to find the defects that Konstantinos was talking about. And this easy approach is based on explicit construction of a defect Lagrangian, which we can do in U1 Maxwell theory, because we know the Lagrangian, the theory is free. So we can explicitly give a three-dimensional construction for this. Let me also say that it's not only the two of us, but this is working collaboration also with Orsela, which is a fellow postdoc at UCL. All right. So we want to put forward a constructive way to look for this non-invertible defect. As I said, as a toy models, we took 4D Maxwell theory and the two-dimensional theory of a compact scalar. And the focus is on codimension 1 defect, so 3D surfaces that act on local operator generically with some invertible transformation. So you can impose that your defect transforms, for instance, f and star f in the Maxwell theory in an invertible way. You take the most general linear transformation, and then you need to impose that defect is topological. So mainly that the displacement operator associated to this defect, it vanishes. And this will restrict the allowed transformation. And once you know which are the allowed transformation, you find the defect Lagrangian that implements them. Once you have the defect Lagrangian, you can compute the action on non-local operators, such as line, Wilson and 't Hooft line, and prove that this action is actually non-invertible. All right, so this is the idea. So this is very simple. You consider a surface S, which is a 3D surface, which splits space-time into parts, S plus and S minus, whose boundaries is S for both of them with different orientation. And so you write the total action in terms of left fields and right fields. Here phi are generic fields. And then on the defect S, you write some defect Lagrangian LS, which in general will be a function of both the restriction of left and right fields on the surface and some collection of only defect field little b. Then you do the variational principle, which usually, which gives the usual equation of motion in the bulk, but then gives some sewing condition on the defect, right? You have condition that you get by varying phi left, phi right, and b, which are written here in the most general case. Okay, this is very simple. You know that, suppose that you know this Lagrangian here, so you compute these sewing conditions, and then you want to check that S it defines a topological defect. How do you do that? Well, if you assume that the Lagrangian on the defect does not depend on the metric, then the condition is that the energy momentum tensor should satisfy this topological condition, which basically means that the displacement operator vanishes. And this is a set of D equation. So D minus 1 is just, so I is the direction along the defect, is just the energy conservation along S, which basically is always satisfied if the defect is a Lorentz invariant. And then the interesting condition is that the perpendicular component of T is conserved, which means that you can displace the defect with no cost in energy. So how do you do this? How do you do this computation? So you realize that phi left and phi right are related according to the equation that I showed before, the sewing condition, and you check if this condition is satisfied or not. If it is satisfied, then you have a topological defect that in our modern approach means that you have a symmetry. Of course, our problem is that we don't know the defect Lagrangian because we don't know the symmetry. We want to look for this symmetry. So we do a reversed approach. So first, we imagine what is the most general relation between phi left and phi right that we can write in Maxwell theory. Then we impose this topological condition. So this topological condition will restrict the possible allowed sewing conditions. And once you have this relation, you interpret them as being given by some defect Lagrangian. So this is basically reverse engineering we start from the topological condition, we go back to the defect Lagrangian. Okay. So okay, let me. So we study Maxwell theory that Kostis already reviewed. So let me just remind you that there are two zero-form symmetry, charge conjugation, which acts on local operator because it acts on F, and S duality at the self-dual point tau equal I, which in this normalization is just E squared equal 1 and theta equal to 0. Then there are two one-form symmetries with charges built with F and tilde F. And the tilde F is the dual gauge field, and remind you that presence of a theta term, there is also a contribution from F to the dual gauge field, due to the which basically encodes the Witten effect. Okay, so this is Maxwell theory, and it has already been reviewed that this theory admits a non-invertible defect at tau equal IN, which Kostis reviewed the construction by composing gauging and S duality in half space. Now, let me also say that there is an easy Lagrangian description of this defect. Basically, the Lagrangian on the defect is simply a mixed Chern-Simons term between the restriction on S of the two-gauge field with some integer Chern-Simons level. And this gives rise to a topological defect which implements an S duality transformation on local operators, because these are the equation of motion on the defect that you get by varying this action. But despite the action being being invertible on local operators, it is non-invertible on lines. So, for instance, the usual S duality is at tau equal I, so you have 1 here, and then of course just exchange the electric and the magnetic charge with some sign. But then if n is greater than 1, the action on lines is given by this combination here, which of course makes sense only if n is a divisor of the electric charge. So you see that all the lines that do not satisfy this condition are actually annihilated by the defect. This is the signature that the defect is non-invertible. Okay, so this reviews how to use a Lagrangian description for this defect here. Now, the question is, can we build other defects for other values of tau? And in order to do this, we use this Lagrangian approach that I described before. So we write the energy momentum tensor in Maxwell theory. And then we write the most general linear transformation that acts on F and star F. So F and star F are related by some linear transformation, and we impose that the energy momentum tensor is continuous at the interface. And what we get is that the most general transformation compatible with the continuity of the energy momentum tensor is an SO2 rotation on F and star F with some arbitrary angle phi. Okay, so this is the most general defect that we can construct. Now the question is there a Lagrangian that gives us this defect here? And once you have the Lagrangian, you can compute the action on lines. Okay, let me analyze separately the case when the sign of phi is 0 or different from 0. So if the sign is 0, you basically have either the identity or minus the identity. These are known defects. So suppose that the defect is the identity, then of course the action on local operators is trivial. The Lagrangian is simply given by a Lagrange multiplier A, which is a defect localized, which is a gauge field, a U1 gauge field localized on the defect, which imposes the condition that the two gauge fields should be equal on S. Then there are other equation of motion that you can derive, and which basically fix this condition here. Not only, of course, F is equal left and right, but also the dual gauge field. But then there is another condition which imposes that the fluxes of this guy should be equal to the fluxes of F tilde. And this, of course, implies that the electric charge from the left and the right should be multiple of this kappa. Now, if kappa is equal to 1, this does not give any constraint, because any line can pierce the defect and just is transparent for the defect because there is no action, there is a trivial action on lines. But if kappa is different from 1, then of course not all the lines can pass through the defect, only the ones that have electric charge, which is 0 mod kappa. And this is precisely the condensation defect, which can be equivalently constructed as the gauging of a Z kappa one-form symmetry on the surface. Now, once you have the Lagrangian, you can also reproduce the fusion rules that Konstantinos explained to us. Basically, that fusing two defects, you get another condensation defect with this integer here, which is the least common multiple of kappa and kappa prime. How do you do that? Well, you just fuse a defect S with the integer kappa, and yeah, defect S with integer kappa, and the defect in S plus delta S with integer kappa prime. Then you take the limit where delta S goes to 0, which implies that now the intermediate field, which lives in the slab between S and S plus delta S, is actually a localized field on the defect. And then you can rescale both A1, A2, and AI, which now is only a defect field. And it's a simple exercise to rescale these guys to rewrite this Lagrangian in this way, which is precisely the fusion rule that was found with the higher gauging procedure. So you have on one side the same condensation defect, but with this integer here, and on the other side, the Lagrangian of a topological quantum field theory for Z GCD kappa and kappa prime gauge theory. Is precisely then the relation here. All right, so far so good. So we didn't discover much. Let me go. The other case is when phi is equal to pi. Then the action is charge conjugation. So the story is the same. Now you just get a plus sign because the action should be charge conjugation. But now you can ask yourself, what about different values of kappa? If kappa is equal to 1, this is just an invertible defect which implements charge conjugation. What about if kappa is different from 1? Is this an independent defect with respect to the other ones? And the answer is no, because you just take the ordinary charge conjugation defect, which is the one with kappa equal to 1, and then you fuse it with a condensation defect at level kappa. You fuse the two of them, you do some manipulation on the defect field, and you get a trivial topological quantum field theory, trivial because there is a 1 here, and the result is precisely this defect here. So the Lagrangian approach allows also to, in some sense, allow avoid overcounting these defects and try to classify the more elementary one. So for now, we have the trivial, the charge conjugation, and the condensation defect. Okay, this was pretty simple. We just analyzed the case where this matrix was the identity or minus the identity. Now what we want to do is to consider the generic case where the sign of phi is different from 0. How do we do that? Okay, so let's go back here. Now, we don't know the defect Lagrangian, we just know the bulk Lagrangian here. So we're gonna vary this bulk Lagrangian and write the variation of the bulk Lagrangian. This will give a contribution in the bulk, which is 0 on the equation of motion, and then a contribution which is localized on the boundary of these two guys, which is precisely S. This variation of the bulk action should be canceled exactly by the variation of the defect action, which we don't know. So let's first consider the variation of the bulk action. This will be a function of the coupling constant, so 1 over e squared and theta, and on all the fields f left, f left, star f left, f right, and star f right. But then we can use this transformation here, invert it, and the final answer will be just a function on f left and f right, and the dependence on these two guys will be implemented through this transformation. So in the end, what you have, do this procedure, and this is the variation of the bulk Lagrangian. So this coefficient here, and left and right and n, are generic function of the two coupling constant, as I said, and of the angle of the SO2 rotation. You can invert this relation that express these three guys in terms of 1 over e squared, theta, and cos phi, and you get this relation here. Okay, so in order to have a well-defined variational principle, we should cancel this bulk action with some defect Lagrangian. And it's very clear that the Lagrangian that does the job is just a Chern-Simons Lagrangian, written in terms of the left field, the right field, and the left-right, the mixed Chern-Simons term. Let me observe that the S-duality defect is a special case of this, because you just take theta equal to 0, and then phi equal to pi over 2, which means that right and left are 0. So 1 over e squared is just n. And these two guys are not there. And this the Lagrangian is the usual Lagrangian of the S-duality defect. And now we can realize more values of this Lagrangian. But at face value, we can only take, because of gauge invariance, integer values for the n left and right and n, which in turn means we can only take integer values of 1 over e to the 4th, yeah, or maybe 4 over e to the 4th, and theta over pi. So the question is, can we do better? Well, we can do better by coupling this Lagrangian to defects field, which lives only on the defect, and which once we integrate them out, this effectively gives a Chern-Simons Lagrangian with a fractional response. This is in the same spirit that is done in the fractional quantum Hall effect. This can be done in many ways. A more structured way is to add the minimal TQFT in 3 dimensions. So we can realize the rational values of this coupling by adding to this Lagrangian this AQP theory, which from the 3D point of view is coupled to a background to form gauge field, which we're taking as a combination of the left and the right field localized on the defect. The important thing about this theory is that the property that we want is that we want to know how this theory transforms once you do a small variation of the background field B, and this is the variation of the action with this variation here. So when you do the variational principle, you can just vary a right and a left. In turns, you know how this Lagrangian here varies. And so you can adjust the coefficients, which are all integers, in such a way that the bulk Lagrangian here is cancelled. In roughly speaking, we are allowing for fractional Chern-Simons levels. So now we don't have to restrict ourselves to the case where theta over pi and 1 over e to the 4th are integer, but we can take any rational, given a Maxwell theory, right, with any rational values of the coupling, we can build this defect with this Lagrangian, and this defect act as an SO2 rotation on F and star F, and as Costi said before, there is a third integer which allows you to build generic values of the cosine of the angle. All right, so good. So we didn't prove yet that these defects are non-invertible, even if you might imagine that. And the way to show that these defects are non-invertible is to describe the action on lines. So first of all, let me say that you know this action here. You know this action here, so you can express not only you can relate F and star F, but also F and tilde F, which in turn mean the electric and the magnetic charge. And you do some computation, and you realize that the action on the electric and the magnetic charge works out to be this. And this is precisely the matrix of SL2Q that Konstantinos showed us with the gauging construction. This is just a consequence on the SO2 relation. This is not a nice SO2 matrix just because the electric charge is not star F, but is tilde F in presence of a theta there. Right, now you can ask, how does the defect act on a line? So let's consider, for instance, the case of a parallel action. You just take a loop on the right with some integer coefficient n and m. You drag it across the defect. And what happens in general, that for generic values of these rational numbers, the line becomes an improperly quantized lines because the charges are not integers. So this means that in order to make sense of this line, it has to be attached to a topological surface. So, and the fact that a loop becomes a disk is the signature of the non-invertible nature of the defect. Right, so for the specific values where these guys are integer, then you get a traditional invertible action. We can also do more. We can do an action on lines which basically allows to consider an infinite line. You have a line on the right piercing the defect and then a line on the left. And the allowed configuration that you can build are the one for which this configuration is gauge invariant, which means that you have to, this requires the presence of some defect operators at the junction, which can be interpreted as monopole operators of the defect theory. So in order to build a completely gauge invariant configuration, the defect should act on the line in a gauge invariant way to produce a left line. And now we can have the case in which there is no gauge invariant junction which is allowed, and this means that the defect is actually annihilating the line. And this is the same that was happening in the condensation defect. Remember that if the electric charge was not multiple of kappa, there was no way that this line could go through. So this line could end on the defect, and so is annihilated by the condensation. But this is far more general and applies also for generic value of cos phi. Another possibility that might happen, that does not happen in Maxwell theory, but happens in other theories, is that there are multiple defect operators which are allowed. So suppose that you can build this configuration with the multiple choice for the monopole operators. Then the action on line is not a simple action, but it is the sum of all possible outcome that can come from the allowed junctions. This is the way that we compute the action on lines, and so in the generic case is a very complicated procedure. So I didn't report the result here, but let me just do a simple example where you just have Chern-Simons theory with integer coefficient. Then you see that the sewing condition here, relating f left and f right and star f left and star f right, impose some specific condition on this integer at the junction. And you work out the action on lines by expressing the right charges in terms of the left charges. And what you get is that sometimes you don't have any allowed configuration. So this is action is 0. And otherwise you have this action on lines if these objects are integer. So if this condition is satisfied. Okay, so this is just to say that you can work out using the explicit Lagrangian the action on lines. And you might have extra restrictions the more defect fields are present in the theory. All right. We didn't manage to compute the fusion rules in the most generic setting because it's a bit complicated to do so. But there are some specific cases where you can do it. And the fusion rule turns out to be just a condensation defect, fusing two of these defects. Okay. Also, let me just mention that okay, let me summarize. So with a simple Lagrangian approach, we show that Maxwell theory has an infinite set of non-invertible defects at this value of tau. And these defects act as local operators as an SO2 rotation with some specific value of the angle phi, where they act non-invertibly on line operators. So the open questions about Maxwell theory still remains a full set of fusion rules. And also if we can make this angle continuous, which would be interesting, but we didn't manage to come up with an idea to do so. And also possible generalization to simple interacting theories to build non-invertible defects for these discrete symmetries. We apply the same game, the same machinery to the case of the 2D compact scalar. So this is basically the 2D analogous of Maxwell theory, which has still a Z2 symmetry, to zero form symmetry, magnetic and winding, shifting phi, and the dual field. There is T-duality at the self-dual point. And if you impose that the energy momentum tensor is continuous, you don't get SO2 rotation, but you just get the 4 roots of unity are allowed. So 0, pi over 2, pi, and 3 pi over 2, which corresponds to the identity, charge conjugation, or well, parity, or whatever you want to call this symmetry, and T-duality. And in particular, we managed to construct a Lagrangian that implements T-duality at generic rational values of R squared. Okay, so that's the Lagrangian construction, and I thank you for your attention. I don't know how did I do with time, but perfect.
So cosinus phi is a rational number between -1 and 1.
Yeah, sure.
And sine should be also rational.
No, sine is not strictly rational, right?
So this, if you consider SO2 rotation.
It's SO2 rotation with a rational value of cos phi, not of the.
So the SO2 matrix, which gives you rotation, only some of the elements will be rational.
Yeah, sure. Yeah. Well, if you take well, for instance, I think the triality defect is an example of this, right?
So the diagonal in this matrix, the diagonal elements are rational, but
Yes.
off diagonal are not necessarily rational.
Yes.
Okay, thanks.
So how much of this structure survives if you add electrons?
Well,
Magnetic one from symmetry should remain.
yeah. You're saying that if I add electron of charge Q, for instance, yeah. Yeah, you can probably, we didn't try. Yeah, no, of course you don't have this duality. So this is why the Lagrangian approach can be useful. My bet it would be that some of them will survive, but I'm not sure about how to.
You briefly mentioned at the end that you hope to extend it to continuous. I mean,
Well,
you
yeah.
have a...
I mean, the point is that if you just look at the Sewing condition for the energy momentum tensor, the only thing that this Sewing condition tells you that the displacement operator of this defect vanishes if this defect acts like this on local operators. It does not tell you that cos phi has to be rational or whatever rational structure. So in principle, these operations are allowed for any cos phi. So the question is, can I find a defect Lagrangian that do this or not?
But presumably it would be something completely different than this A and P theory.
Yeah, I mean, I think so. Whereas in the T-duality cases, everything is easier because you don't get a continuous of transformation. You just get T-duality and Z2.
Further question? No? You want to ask it?
So if I want to ask again about the magic values of tau. If I consider an interface between two different magic values of tau,
Yes.
can you say anything using this technique about what's living at the interface?
Yeah, it would
So a
be
stupid example, 0 and pi, obviously, but
yeah. I think these are closed. So if you fuse two defects with two different defects with different values of n left and right and n, you get another one of this kind with different values of n left and right and n. So notice that if I tell you the action on lines, I'm not telling you the defect Lagrangian. This is like the condensation defect, right? If I tell you that a defect acts trivially on a line, you don't know what is the Lagrangian. So sorry, I wanted to say a different thing. If I tell you the action on local operators, you don't know the action on the lines. So if I tell you that the defect acts trivially, you don't know if it is a trivial defect, a condensation defect with ZK, a condensation defect with Z2K, you have no idea. So when you fuse two different defects, you might get different. I mean, there is much more space in the space of Lagrangian than there is in n left and right and n, is what I want to say. So my guess is that this is closed under. This is the best you can do, right? So it has to be that. I don't know if there is some arithmetic properties of tau. We try to break our head on this, but
I have a follow-up question to my previous question. So if you fuse the defects, these SO2 matrices, are they supposed to multiply?
yes.
So how can, if you have a pair of matrices with diagonals are rational numbers, but all diagonals are irrational numbers, this property doesn't seem to be preserved. I mean, if they all would be rational, I understand this is a SO2Q group. It's a group.
Yeah. You could ask the same. Sorry. You could ask the same in the triality defect, right? Which is tau equal 2/3 pi, right? And the value of 1/e² is not rational there, I think. I mean, Oh yeah, okay, yeah. Okay, yeah. Sorry, yeah, you're right. Yes.
Well, I think it's a bit. I mean, if it's SO to Q, I mean, it's like group of rational. I mean, if all elements are rational, it's a group of rational numbers on a circle. It's not. It's actually more complicated, I think, than Q. Yeah.
So is the claim that you can essentially imposing these sewing conditions, you can figure out all symmetries of a given system, or codimension one,
much.
say codimension one.
Yeah.
If you impose the
Codimension one is important because we
Yes.
need a defect that separates the space-time to impose.
but
the
just
sewing
from
condition.
knowing the energy momentum tensor and imposing that it is conserved and preserved
Yeah,
this
the problem is that
sewing condition, you
the problem is that it's not obvious. So Maxwell theory is a bit special because the fundamental degrees of freedom are gauge invariant F left and F right, right? In non-abelian gauge theory, this wouldn't work.
Mhm.
So if you ask how SL2Z act on in non-abelian gauge theory, it will be more complicated to build it with F and F left and F right because they're not gauge invariant. So at this level, it works for a very specific and simple class of theories. I would say that one can do better maybe starting with scalar theory with some Z2 symmetry and see if this works in this case, but I would not go as far as claiming that this can work every time. Maybe
Thank
there is a way, but I'm not sure.
Assuming that the defect has a continuum Lagrangian description, no?
Sure.
Which is not obvious.
Yeah. No, indeed, you can maybe you can make the angle continuous, just you don't know the Lagrangian description of it.
No, because what you do, you find the Lagrangian, which is
Yeah.
Chern-Simons.
Yeah.
That's when the n's are integer, it's sensible, quantum mechanical. This is a classical computation.
Yes,
no?
this is all classical because the theory does not normalize. Right?
No, quantum mechanically, if n is a real number, it's not a rational number, you don't know to make sense of that. And when it's rational, you know this trick. But for me, it's not obvious that all the topological defects of a theory have a Lagrangian description
I agree.
as an integral of something.
Yeah.
But for sure, those you can get like
I agree,
this
yeah.
with the method.
Sorry, is the swing condition equivalent to ask that the action is invariant under some transformation?
Yeah, it's equivalent to ask that the displacement operator vanishes.
But
It's basically the variation of the action with respect to a small shift on the embedding of the defect.
I'm asking that if you take Maxwell,
Yes.
you see
no.
as a classical theory, it is invariant under SO2 rotation.
Well,
And
but
this is the same condition that you find for swing.
at the classical level, you're saying.
I think that at zero form symmetry, usually you see the action and find the,
Yeah.
the symmetry of the action. Yes, but classically still SO2 is a symmetry of Maxwell. Then you say that the flux is not conserved, and so
Yeah, the action on A is not necessarily well defined. I mean, in a Lagrangian way.
Any other questions? Okay, if not, let's send the speaker again.